Hello, everybody. Let me get my drink. Microwave is yelling at me. I'm humming a song which is in my head now because it is a song that has been in the spotlight, sung by Indian Idol contestant Amrita Rajan, and I'm a big fan of hers. And so, anyways, that's what I'm humming at the moment. But good evening, good morning, good night, good day, my loves. We are here, we are live. So, I would like to say welcome one and welcome all. Is the light on? Yes, the light is on. Thank you so very much indeed for all your support, all your likes, shares, and subscribes. If you are here in the live, then welcome, welcome so much. And please do say something in the chat so I can say hi to you personally, exclusively, and feature your username as a shout out. Also, if you're seeing this as a video upload later on, please do leave me a comment. Always appreciate reading your thoughts, comments, messages, and whatever ideas you want to share. And tonight, hello, Steven Ice. Hello, J. Manuel has sent a flower. Thank you so much for the gift, J. Manuel, and thank you so much, everybody, for all the gifts and super chats. As always, hopefully, we go to the next level of such things tonight, and that really helps me to sustain the channel, and all your support means a lot to me personally and to the kitty cats that I support as the matriarch of this household. Hello, J-Dub. Tonight, by the way, we're gonna have a very exciting discussion on Einstein and his work, which will, I think, illuminate a lot of topics that have been coming up lately, that people have been enjoying, and also at which it would be good to look at further and kind of give it a further bit more clarity and clarification. So I'm excited for that. As soon as a few more people join, we will get going. I do have to wake up a bit earlier tomorrow, so I don't want to go super late tonight. So I really appreciate all of you joining and showing your support. And thank you so much. Hello, Stephen T. Eyes. Number one right now is Stephen. So let's see, the top fans. Number one is J Dub. Number two is Stephen T. Ice. And number three is J Manuel. J Manuel has sent a gift. And everybody is saying hello so far. So I do appreciate that. Thank you so much. Let me share the live and do some settings over here on my laptop. Give it a second for the top fans to kind of settle down because it's probably still thinking and analyzing. Don't worry, guys. If you see the things and it doesn't make sense, it's because we just got started and I still have to share the live and things like that. So I'll be right back with my other phone. Hello, everybody. Let me turn that on. Please do like and sub. Oh, I see my own chat message. Great. Perfect. Okay, and so because we're gonna cover Einstein and his work, I have specifically decided to feature a bunch of Einstein-related shopping links. If people are interested, I know that that is just an option, not to worry either way. Okay, and then let's do a goal for this live. What should my goal be for this live? Let me do a goal. Let me do a big goal. How about that? A big goal. A big goal. It's not even that big of a goal, but let me do a big goal. Hello, everybody. Thank you so much for joining. Can you please like, share, and subscribe? Hello, Steven. Hello, J-Dub. Hello, J. Manuel. Hello, everybody that is joining. I just started a goal. A goal. A goal. Please, can we like and subscribe? And can we get 10 likes? Can we? Can we? Can we? Can we? Can we get 10 likes? So tonight is the night where we review and oh, thank you so much, Stephen T. Ice. Stephen T. Ice 1969 has done a thumbs up, a gift, not a super chat, but a gift. Thank you so much, Stephen. There's also gifts, there's also super chats that people can do. Thank you so much. Very indeed, very indeed. So I want to start off by, first of all, welcoming and thanking everybody from all of the continents as per usual. South America, North America, Asia, Africa, Europe, Antarctica, Australasia. Did I miss anybody? Please let me know. Africa, Madagascar, some of the regions now we will be naming as well. Caribbean islands, Dominican Republic, Puerto Rico, Hawaii, although that's a state now of the US, but you know, it used to be a queendom. So there is that. Um, thank you, J-Dub, for sending the floating heart. Thank you, Sarah Mitchell. Hello, my lovely person, Sarah Mitchell. Good to have you here. Please do like and subscribe and keep coming back to these lives, okay? Let me also thank Sri Lanka, Nepal. That's the food I ate today, Nepali food. India, my birthplace. Pakistan, Afghanistan, Iran, I don't know, Doha, the airport that we use a lot to fly through to go to India, things like that. So welcome, welcome, welcome. Welcome, 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 welcome one and welcome all to this live stream episode featuring Baji and Physics. I am Baji's mother. Baji is a kitty cat. On this channel, we feature kitty cats, my face, and a ton of physics, astronomy, astrophysics, and cosmology presented by me and my face. And so I hope you do enjoy, and I hope that you stay through the entire episode because we go for pretty long episodes. Tonight's episode might be just about an hour or so because I have to wake up early tomorrow night. But some of the episodes are actually 3, 4, 5 hours long, and you should go and check under the live tab of my channel called Baji and Physics to see all of these previous episodes. We have been doing these lives for over a year now, and many topics have been discussed already, especially in physics, cosmology, and astronomy type of topics. Pretty much every major topic under those categories have probably been discussed already at least once, but we always are willing to learn more and more and to share more and more and to explore with everybody. And I especially appreciate all the questions and really nice comments and thoughts that I get from the audience whenever we do go live. Sponge is asking, are you married? Damper is asking, do you have a wife? I don't have a wife, but I definitely need one. I have to be my own wife, which is quite challenging. See how I'm always running around with a lack of support? That is because I have no wife. I thought you would know that already. J. Manuel, thank you so much for the super chat. I really do appreciate it so very much. See, I depend on these super chats and these gifts and such, and I go around trying to do my best, which indicates that there is no wife in the picture. Okay. Thank you so very much indeed. But I do have it better than many people because I have no husband. So there is no energy being spent in that direction, and all of the extra energy that I thereby have, more than married women, I spent on this channel with you guys teaching physics and bringing awareness to the scientific channels. And we do science presenting and science communication along with some kitty cat fun times and cuddles and purrs. And with my face now. I used to do faceless lives a lot, and we also covered books of various natures, like even literature or murder mysteries, which are some of my favorite books for fun. But then physics is my background. It is what I have 3 degrees in. So I started to cover those physics topics, and people seem to appreciate. And so now we kind of have these sort of lectures, if you will, or study meetings, study with me lives for a while at this sort of odd hour in the night here on the east coast of the US, but it works out for other time zones. And so if you're in California or Asia, then it's a perfectly good time and whatnot. So, we try our best, and I do appreciate that you are here, okay? Please do put something in the chat. I love to hear your comments and get to know you better. J. Manuel is now number 1. Intru is saying, I support you. Thank you, Intru. Mike Io is saying, well, hello there. Hello, Mike Yo. Not Mike Io. Mike Yo. Hello, Mike Yo. Hello there to you too. Sponge is saying, science was always fun. It is. It is fun, fun, fun. So we will get started very shortly here. Let me fix the description of this live, okay? And give people a few more minutes. If you have any questions, now is a great time to put it in the chat so that I can see it and try to answer it quickly before starting with the topic for tonight. By the way, we will be using the book Einstein's Cosmos by Michio Kaku. This is a book that we have extensively covered already on these lives in the past, but it was over a year ago when we were regularly talking about the topics from that book. And Michio Kaku, of course, worked on, I believe he worked on string theory a lot, and also he has written a very nice sort of documentation of Einstein's experiences and work. This book is called Einstein's Cosmos: How Albert Einstein's Vision Transformed Our Understanding of Space and Time. So he's also a good person to read in terms of explaining sort of the debacle between general relativity and quantum mechanics. Sort of the lack of let's say alignment between those two topics, and some of the discrepancies between those topics and debates between the people with those topics is something that we kind of have mentioned in the past, but it might not have been totally crystal clear. And I think what we're about to cover tonight will definitely clarify further. Okay, so thank you so much. Hello, J. Franks. J. Franks is saying, hi, Sugar Plum. Well, hello, J. Franks. Sponge is saying, did you like Interstellar? Yes, I did. I do love Interstellar, the movie, and especially the music. Can we get 10 likes? Scott Bromer is saying, take us to school. Yes. We are here to do that. Francisco Pascual is saying hi. Hello, sorry, says Lucifer loves you. Hello, Lucifer. How are you doing, my heart? Hello, Taj. How are you doing? Okay. We are covering... I'm just updating the description here. We're covering Michio Kaku's... I don't know if you guys have read this book, by the way. If not, it is highly recommended. I don't think I found it under the YouTube shopping links, but it is called Einstein's Cosmos by Michio Kaku. And let's see. Kaku is a skillful and genial popularizer. While this is fully a biography, succinctly visiting Einstein's difficult childhood and unpromising early career, his two marriages, and his emergence as a 20th century cultural icon, the guiding thread is undoubtedly the evolution of his ideas. So it's a good book that it's a good book that makes clear certain difficult topics, and that is why I really like it. Okay, so we will be using it. We are covering. Okay. It's a little bit quiet tonight. I am wondering where everybody is. If you could please share the live, that would be amazing. Okay. Scott, are you here? And Reese, are you here? Thank you, Jay Franks. Hello, Adam. Okay, perfect. I'm glad that some people are here. Okay. Okay. I will also share the live from the other phone. So let me go get the other phone. Hello, Jose. Hello, Abel. Hello, Scott. Hello, Adam. Thank you so much, guys, for joining and saying something in the chat. Really appreciate it. I'm drinking a warm drink from this Cat Mom mug. Okay. So, let me also turn the heat up. So it might be best if I start the reading and then give you some explanations along the way. Now, chai tea? No, this is actually Horlicks. What I'm drinking is this thing. This is from an Indian grocery store. I don't know if you know about this drink. It's not sponsored, but this is a drink that we grew up drinking in India. Okay, it's a malt, basically, and it's kind of like, it's not really a chocolate drink, but it's along those lines. And it has protein in it. It's like advertised as being good for kids in India, and they grew up drinking it. And it's like this drink that you drink in the winters. So I bought it from a grocery store because, first of all, it reminds me of my childhood and India. But it is a nice warm drink to have while doing this. And I don't believe it has any, caffeine. It's not like coffee or tea. What a beautiful dress. Oh, thank you. This dress, I forget where it's from, but I've had it for a while. It is probably from... It's probably from TJ Maxx or Marshalls, to be honest, because I like myself a deal. Thank you. Scott is saying New Year's drink you had that night. New Year's drink, New Year's Eve, I had a wine. I had a red wine on New Year's Eve. We can do that towards the end of this live if you want. But I had a little wine at the end of New Year's Eve as a special occasion. I don't do that all the time, though. I don't do it all the time. I have a little wine that we can do at the end, perhaps. Shannon is saying pretty hair. Thank you, darling. Sponge is saying, where can I get that? This is, you will find this in an Indian grocery store. Especially in the wintertime, they should have it. And if not, then here it is. Look for it. It's called Horlicks. Horlicks. Hello, Joseph. We're studying Einstein's work tonight, okay? So we're going to start with a bit of special relativity discussion, but not too much into that. But then we'll go into... general relativity, okay? but in a popular science kind of way. So it won't be very difficult to follow. It should be very pleasant reading, and it should be like a very smooth read. Nothing too difficult, okay? But it does make us aware of and sort of familiar with those topics of relativity and Einstein's work in 1905 through 1915, 20th century stuff. And really, this was a major, basically the 20th century is a very rich 100 years in physics. We saw the rise and the basically gift of relativity, first special theory of relativity in 1905, and then general relativity being developed by the time it's 1915. And then the first signs of string theory or extra dimensional type of mathematics to kind of extend relativity to explain more things in the form of Kaluza and Klein's work in 1919, as early as 1919. But then, of course, there was a bit of a pause, and they didn't really continue with string theory until much later in the 20th century. But, you know, still like 50s, 60s, of course, is still the 20th century. So all of this is happening in classical physics, as I like to put it. And then also remember developments with a very important person in astronomy, Hubble, doing his observations and really opening up our eyes quite literally to many, many more galaxies and the universe really at that point. And we got the first clues of expansion of this universe. And by the time it's 1998, which is very much, towards the end of that century. Even I'm born at that point. So I guess me and Einstein shared a century, but the opposite ends of it. That's too bad. But I am from the 1900s as well, guys. So in the 1900s, by the time it is 1998, remember we spoke about how this expansion of the universe was very much a thing in cosmology. It's something that we are aware of, and we are even measuring and confirming, and we're finding that the expansion at especially the large distances away is speeding up, and those people who confirmed this got the Nobel Prize. It was a big deal. Whereas earlier on in that same century, remember when Einstein is developing his general theory of relativity in 1915, by the time it's 1915, there is no notion of really an expansion of the universe. And in fact, he introduced the cosmological constant, remember, to stabilize the universe against gravitation. And he included the cosmological constant in general relativity as a anti-gravity term that will balance out gravity and make the universe static. Now, later on, with Hubble showing that actually the universe is expanding, he felt a little embarrassed, and he called the cosmological constant sort of a blunder, a mistake. But actually, the cosmological constant, the way he introduced it, is still considered to be sort of the foundation of today's research topic, and something that we still don't obviously understand, and is still very much an active area of research, which is of course dark energy, and what it is, and all we know is its effects, which is that it makes the universe expand. So expansion of the universe sort of has a birthplace in Einstein's general relativity, maybe kind of unwittingly, but at the same time, it's one of his geniuses, actually. You know, when a genius like Einstein makes a mistake, even in that mistake there is value, and exactly that value is to be found in the cosmological constant, which also we have talked about a lot. And today's topic is not going to be totally focused on that, but I did want to mention that the cosmological constant is as old as general relativity, and at this point today, even right now, in modern astronomy of the 21st century, we are setting up huge and big experiments, collaborative efforts to find out more about dark energy, or what causes this expansion of the universe. So it's still a question mark. It is still a mystery, and an unsolved mystery, and a research topic. But the seed of it, the idea of it, is as old as general relativity, which is, of course, now over 100 years old. Now, I wanted to also mention about sort of these developments of the 20th century, because once again, 20th century is really rich. I wasn't really done listing off everything that important that happened in the 20th century. The other side of things that also happened, which we'll read about a little bit tonight, is quantum mechanics and the development of quantum mechanics and the gift of the physics of the very small, or quantum mechanics, that we started to also see really take shape. And the founding fathers of quantum mechanics did some of the best work in the 20th century. Planck, Niels Bohr, all these people, they were up against the classical physics camp. The classical physics camp was the relativity people, later on becoming the string theory people, etc., etc. And they really did not like quantum mechanics to begin with. There were a lot of really bizarre things about quantum mechanics, and today we kind of accept a lot of this sort of like nothing. Sort of, we've gotten used to the sort of bizarreness of quantum mechanics, and we see people embracing it, and people even wanting to apply it, and things like quantum computing, all those types of things. But when quantum mechanics was getting developed for the first time, I mean, remember, there was a time when people thought that the most fundamental unit of matter was the atom. They didn't even know about the nucleus, and the fact that the nucleus has protons and neutrons, and those things, protons and neutrons, further break it down into quarks. So just imagine how much new information quantum mechanics has brought about in a short span of time, and just kind of shocking people with all its news constantly. So I think at some point, even Einstein was probably a little bit tired of the fact that quantum mechanics keeps shocking your system and keeps kind of going against the grain. And the biggest way in which it really went against the grain was the fact that there is this uncertainty principle, or a probabilistic nature of quantum mechanics. Okay, so when people generally, traditionally did physics, so this is where we kind of classify these two things, as one is classical physics and the other is quantum mechanics. Classical physics has also developed. General relativity falls under classical physics, but think of it as more sort of classically accepted, or something that is more traditionally done, whereas quantum mechanics kind of just breaks all of that. And it is the physics of the very small, just everything just breaks down and is completely different. So when I say classical physics, I mean relativity, superstring theory, Newtonian mechanics even, okay? Because Newtonian mechanics is basically the older classical physics. When I say quantum mechanics, of course, you understand I'm talking about quantum mechanics, which is not classical physics. See, in classical physics, when we write down an equation, when people want to know, say, the position of the moon as a function of time, or the position of a black hole as a function of time, or the position of this galaxy as a function of time, like the position of, say, our solar system as a function of time. We know that the solar system is orbiting our galactic center. We want to be able to write down this equation with a level of certainty and confidence, classically speaking. Okay, we don't like to think that that answer could be sort of probabilistic or uncertain. Okay, so people, basically physics, in one way of looking at physics is that people like to write things down as a function of time. The people want to know the position of Joe as a function of time. Now, Joe can be the moon, Joe can be the sun, Joe can be this galaxy, Joe can be a black hole. But we want to know where Joe is as a function of time. And we want a darned equation that just clarifies it, and it's like set in stone. I mean, not really, because it's moving, changing with time, but like things like that, basically. But in quantum mechanics, we cannot do that. We can only have the probability of finding Joe, where now Joe is an electron, or Joe is a neutron, or Joe is a proton, or Joe is an atom, or Joe is some other, a quark maybe. So when you come to the physics of the very small, you end up with probabilistic answers. You do not end up with deterministic answers, okay? And we cannot know certain things for certain anymore. And there is an uncertainty inherent in nature, because when you use a photon to look at an electron. See, the thing is that photon is a particle and electron is a particle. Let's say now we're in the world of where Joe is a photon or an electron or a positron or a quark or something. Well, these are all particles. At the particle level, a photon could disturb Joe. One single photon, and especially depending on the energy of that photon, it can really disturb Joe, and now, because you're looking at Joe with that photon, Joe has changed, and and there's uncertainty inherent in your measurement of Joe. Joe's position, Joe's velocity, uncertain like, very uncertain like, okay, probabilistic like. And this is something people were very uncomfortable with. People did not like this. The classical physicists camp of people who were the main people until quantum mechanics rose, they were like, what is the point of a science where we cannot get full answers and deterministic answers? And what is this, nonsense, basically? So really, quantum mechanics could have been kicked to the curb and probably disappeared and been, dumped, basically. But it is to the credit of quantum mechanics and its fathers and mothers that it kind of survived all of that criticism, and it continued to continue with so much experimental success that people had to pay attention to it, and people had to accept it eventually, even if people didn't like it. Some of the developers of quantum mechanics themselves didn't like it. So Schrödinger, for example, did not like how quantum mechanics ended up being, like he wrote down the wave equation, Schrodinger's wave equation, but then once he realized that wave equation actually only makes sense when you realize that gives the probability of finding the electron and not the electron's position versus time, then he didn't like quantum mechanics all that much anymore. I mean, at least as far as I'm told. So even the people who contributed heavily to quantum mechanics had a lot of discomfort with quantum mechanics. So if you're somebody that kind of struggles with quantum mechanics, just know that even Einstein struggled with quantum mechanics, and even some of the contributors of quantum mechanics struggled with quantum mechanics, such as Schrödinger. And then he went to, I guess, either Ireland or Scotland or something, somewhere north, to to get away from Germany, I believe, if that's where he's from. Just someone look that up. But basically, and Einstein, of course, came to the U.S. Thank God, right? So, so yeah, and also remember that in the 20th century there were 2 world wars. That also affected some things. As far as I understand, of course, I wasn't around at the time, but I would only imagine that it was actually very disruptive to a lot of science, and also kind of changed the direction a lot of science, such as things were at some point, of course, there was this race to come up with the atomic bomb and things like that, and the science that was done in Germany versus the US at that time was greatly influenced by that. Pretty much all of the scientists were called on, except for Einstein. This book talks about how Einstein was actually not involved in the development of the Manhattan Project, and he, of course, they used his E equals mc squared, but he was not directly consulted for that work. So because they didn't trust him yet, because he was a relatively new immigrant in the country. So anyway, those are, something else. But basically, a lot kind of happened in the 20th century. Relativity developed, one main thing. another main thing is quantum mechanics developed. But the thing is that these two things, relativity and quantum mechanics, don't really totally agree. In fact, they don't agree. They're both wrong to some extent, and at certain things they're kind of wrong. But relativity does well with describing gravity at large scale, and with a lot of success, and quantum mechanics does well at describing physics of the small to a large extent. So both have tremendous experimental successes, is why we keep both around. But the people also, it turns out the people who work on one don't really work on the other one, so they don't have to meet much, and that's probably how the peace is kept. But at the same time, just know that because there are certain discrepancies between the two, it motivated people to come up with a whole another theory which would unify these two and be sort of its own theory that kind of subsumes general relativity and quantum mechanics. Okay, so this is why you got something like superstring theory as a candidate for that. So just keep in mind about that motivation as we launch into this topic. Okay, hopefully all that made sense. I know that was a lot to throw at you. Hello everybody, thank you so much for the gifts and super chats, really appreciate it. Hello, Stay Curious. Hello, Josh. Spooky action. Oh, love it. Your own. So you're so old if you share his time. I'm from the 1900s. Yes, I am. I mean, aren't you? Why do you believe... Thank you for all the hearts. Thank you for the love. Thank you, guys. Hello, Abraham. Hello, Joe. Yes, theory of everything. Somebody said theory of everything. Yes, indeed. That's exactly right. Hello, Shergill. Okay, thank you so much. Really appreciate all the comments and questions and chat messages. Let's see. What is this? I'm trying to just skim really quickly to see if there's any questions I can answer quickly. Can a black hole, let me see. Thank you, everybody. So I see a lot of comments. Sorry, it's a little hard to keep track. Let me just read off the top fans really quickly before I move on to the reading and the topic, okay? Number 1 is J. Manuel. Thank you so much, J. Manuel, for doing a gift. Number 2 is Steven Sky. Hello, Steven. I didn't see you in the chat, but I'm sure I missed it, and thank you for being here. Number 3 is My Music Gen X. Number 4, hello, My Music Gen X. Always glad to see you. Number 4 is IMMC Guy. Number 5 is Big Daddy Rod. Number 6 is Sam. Number 7 is Jay Franks. Hello. Number 8 is Julian. Number 9 is Awaken My Ear. Okay. Number 10 is Zevant. Number 11 is Shergill. Number 12 is Abraham. Number 13 is Adam. Number 14 is Corrupt. Not too corrupt, I hope. Number 15 is Joe. So thank you so much, everybody, for being here. Please do like, share, and subscribe. Can we get 40 likes? And I will now get started with the reading from the book Einstein's Cosmos by Michio Kaku. Without further ado, but I hope that my sort of spiel at the beginning helped with some of the sort of backdrop of what we're talking about, and especially to kind of summarize the 20th century. There was there was relativity, including special relativity and general relativity being developed. There was quantum mechanics being developed. There were two wars. There was Einstein. There was Niels Bohr. There was a debate between them two. String theory is technically as old as 1919, but it wasn't developed until later. Superstring theory is a grand unification theory candidate, which, of course, hoped to unify quantum mechanics and general relativity. But it is still just a candidate because it is not testable. And by the end of the 1900s, we had proof that the universe was expanding. And not only that, it was... the expansion was accelerating. We had proof of the fact that it was expanding even earlier, of course, when Hubble gave us observations in astronomy of the universe and many, many more galaxies than we ever imagined to be present. So Hubble's really important. Cosmology really came to be and started to develop as a modern science, the study of this universe, and we really started to pay attention to the sort of different stages of the universe and the different eras of the universe. And the Big Bang Theory is consistent with, of course, expansion of this universe. So I think I've covered sort of in a nutshell about the 20th century as best as I could. If I missed anything, I am sorry, and we will, I'm sure, come across it in this book, in this part of the reading, which will solidify and clarify some of the things that we have been talking about in earlier lives as well, where I kind of alluded to this issue between quantum mechanics and relativity, but maybe didn't go into a lot of detail in these immediately past lives, but in other lives, in the more past, we have. Okay, so let's just get going here, because I think it will be illuminating. Okay, this is Einstein's Cosmos by Michio Kaku, and this is chapter 7, and it is called Unification and the Quantum Challenge. So it's a very promising chapter title because, of course, we care about unification at this point. Once you have relativity and once you have quantum mechanics as two characters in the story, then, of course, unification comes to mind. And once you have quantum mechanics anywhere in the story, of course, we have a challenge. So I like that title a lot. In 1905, almost as soon as Einstein worked out the special theory of relativity, he began to lose interest in it because he set his sights on bigger game, general relativity. In 1915, the pattern repeated itself. As soon as he finished formulating his theory of gravity, he began to shift his focus to an even more ambitious project: the unified field theory, which would unify his theory of gravity with Maxwell's theory of electromagnetism. It was supposed to be his masterpiece, as well as a summation of science's 2,000-year investigation into the nature of gravity and light. It would give him the ability to read the mind of God. So basically, in 1905, he worked out special theory of relativity. 1915, he had already done general theory of relativity. General theory of relativity is the upgraded, updated, latest, and greatest theory of gravitation, giving us more accurate answers than Newtonian gravitation. Okay, so you would think that this is quite enough work, but Einstein just kind of kept moving his goalpost. Ambitious person, right? And of course, it's sort of like the more you know, the more you realize where you don't know something. So he probably got to the general theory of relativity and realized, well, I have this gravitation thing down, but I don't have a way to unify it with electromagnetism. Now, also keep in mind that those were the days when we might not have had all of the information available to us to unify everything. But this was what he wanted. So we have to understand his motivation and his ambition. And by the way, this grand unification theory business is something that he died trying. So you can see how if somebody like Einstein really cared about this is not sort of what do you call it? This is not like a trivial goal. There is a lot of motivation for it, but it is also really difficult. Okay, and we will kind of probably see some of that difficulty here. Einstein was not the first to suggest a relationship between electromagnetism and gravity. Michael Faraday, working at the Royal Institution in London in the 19th century, performed some of the first experiments to probe the relationship between these two pervasive forces. Ultimately, these are the two long-range fundamental forces, the other two fundamental forces being weak nuclear force and strong nuclear force, which are not, found at that point. So I guess they didn't worry about it, but they did know about electric charge and magnetism and how, electromagnetism is a thing, and then there is gravitation. So they wanted to kind of understand how to bring these together. He would, for example, drop magnets from the London Bridge and see if their rate of descent differed from that of ordinary rocks. If magnetism interacted with gravity, perhaps the magnetic field might act as a drag on gravity, making the magnets fall at a different rate. He would also drop pieces of metal from the top of a lecture room to a cushion on the floor, trying to see if the descent could induce an electric current in the metal. I love Faraday, by the way. He's a very, I love that Faraday is such an experimental guy. I think he might be one of my favorite experimentalists. All of his, electric field and magnetic field contributions, of course, come from him working in the lab a lot, which I really like. Thank you so much, everybody, for all your likes, shares, and subscribes. Can we get 50 likes? Thank you, Derby. Thank you so much, everybody. Please do subscribe as well. Mr. Drew, hello. Okay, so they do shake, so Faraday noted, they do not shake my strong feeling of the existence of a relation between gravity and electricity, though they give no proof that such a relation exists. So he had this strong feeling that these two fundamental things had to be related in some way, and he was trying and trying to show that, but he just couldn't find that relationship. Okay, but he tried. And I mean, these people, remember, they had done a lot of work already. They had each reached sort of pinnacles of their career. At the, by the time it's 1915, 1916, Einstein is super, he's very successful guy, and so is Faraday, because electromagnetism is even older. Electromagnetism, electric field, magnetic field, all that stuff happened in the late 1800s, and then Einstein gave us the major insight into electromagnetism with his special theory of relativity, giving us the speed of light in vacuum is a constant in 1905. So by the time it's 1905, Faraday and all these people, they're well settled in their careers, and still they're trying. So that's another thing to note. I feel that some of these great minds, they don't really stop after they have reached a certain top of a mountain. They kind of see, they have the better view at the top of the mountain, right? And they use that height to see even more, and they see where there are gaps even better. And so it's a little hard to be these people as well, because it's not like they will just stop, and you do feel sympathy for when they fail at something, because it's hard. Furthermore, Riemann, who founded the theory of curved space in any dimension, believed strongly that both gravity and electromagnetism could be reduced to purely geometric arguments. So Riemann had Riemann is very well known in mathematics, and so he basically thought that these two things could just be geometric arguments. Einstein was a person who liked to find the physical reality and the physical meaning of things. He wasn't just a geometry guy, but that's how Riemann. Unfortunately, he did not have any physical picture or field equations, so his ideas went nowhere. Einstein once summarized his attitude toward unification by comparing marble and wood. Marble, thought Einstein, described the beautiful world of geometry in which surfaces warped smoothly and continuously. The universe of stars and galaxies played out their cosmic game on the beautiful marble of space-time. So as you know, gravitation is curvature of space-time. That is what he gave us in Relativity. Wood, on the other hand, represented the chaotic world of matter, with its jungle of subatomic particles, its nonsensical rules for the quantum. According to Einstein, this wood, like gnarled vines, grows in unpredictable and random ways. New particles being discovered in the atom made the theory of matter quite ugly. So they thought that quantum mechanics was quite ugly, these classical physicists like Einstein and company, okay? Einstein saw the defect in his equations. The fatal flaw was that wood determined the structure of the marble. The amount of bending of space-time was determined by the amount of wood at any point. So even if you didn't like all this stuff that was happening in matter, because quantum mechanics, matter waves, writing down the equation of motion for an electron is matter after all. Turns out that equation is going to just be a wave equation, and that wave equation actually gives you the probability of finding the electron, blah, blah, blah. Those types of things, right? But matter, after all, is what, a massive object is made of matter. So even though this massive object, bending space-time, all that made sense in general theory of relativity, when you go into the massive object and you go microscopically into it, and you investigate the physics of the small things that make up that massive object, then you have to deal with something ugly, according to Einstein, okay? So to Einstein, his strategy was clear: to create a theory of pure marble, to eliminate the wood by reformulating it solely in terms of marble. So he wanted a theory that would be kind of consistent and would not require quantum mechanics or anything ugly to describe everything. So if the wood itself could be shown to be made of marble, then he would have a theory that was purely geometric. For example, a point particle is infinitely tiny, having no extension in space. In field theory, a point particle is represented by a singularity, a point where the field strength goes to infinity. Einstein wanted to replace the singularity with a smooth deformation of space and time. So this singularity business is sort of a limitation of that mathematics, okay? Imagine, for example, a kink or knot in a rope. From a distance, the kink may look like a particle, but close up, the kink or knot is nothing but a wrinkle in the rope. Similarly, Einstein wanted to create a theory that was purely geometric and had no singularities whatsoever. So he was aware that having that singularity was a flaw, and he's like, is there any way to kind of turn this into sort of a wrinkle, some other way of describing that thing? And that was one of the goals, because nobody likes their theory to have a singularity, right? It's not like they're not aware. It's not like he was not aware of the limitations of his theory. He's the one who worked on it along with others. And if there's a singularity, like classically there's a singularity inside a black hole, classically there's a singularity at the Big Bang, at the origin of this universe. Those things are not enjoyed by classical physicists or by anyone. It's just a limitation of the math, okay? So if somebody can mathematically and physically come up with a better explanation, then of course that would be welcome. Of course, they'd have to kind of be consistent with everything else as well and whatnot. And that is where I think a lot of this challenge will be. But anyways, subatomic particles like the electron would emerge as kinks or some kind of small wrinkle on the surface of space-time. The fundamental problem, however, was that he lacked a concrete symmetry and principle that could unify electromagnetism and gravity. As we saw earlier, the key to Einstein's thinking was unification through symmetry. He was a very beauty-seeking kind of guy. He liked the beauty of nature and the symmetry of nature. And it is true that there is some very beautiful natural symmetries that do exist. You know, like string theory is supersymmetry. So, you know, that super word comes from supersymmetry. So even string theory, which is of course not testable and, you know, whatever, but even superstring theory depends on certain symmetries and certain beauties that we are assuming exists in nature. And Einstein was very much sort of that type of person. He didn't like nature to be ugly, okay? With special relativity, he had the picture that guided him constantly, running next to a light beam. When he worked on special theory of relativity, he had a thought experiment. He had a picture in his mind that he was running next to a light beam. And was he ever catching up? Was the speed of light, according to the person running next to a light beam, ever different? And he realized that no, the speed of light in vacuum is a constant. Even if you go at 0.9 c, where c is the speed of light, you would still experience c as the speed of light, which is really deep. You know, it sounds simple, but that is actually what changed everything in 1905. So, but he had that picture to work with. His imagination and his sort of the way he was wired saw that. But the way he was wired was now struggling to find a way to unify quantum with the relativity, okay? So this picture revealed the fundamental contradiction between Newtonian mechanics and Maxwell's fields. From this, he was able to extract a principle, the constancy of the speed of light. Because see, in Newtonian mechanics, I'm sure you've done it. Like there's, you know, we've all done the Newtonian mechanics problems of like, this train is going this at this speed, and there's another train, and they will kind of experience each other's, you know, relative speed and whatnot, and like you could do the math of when you'll pass, or you know, you've been in a train and seen another train, right? Like if they're coming from the opposite direction, then it goes by really fast when you're passing, right? And if they're going in the same direction as you at sort of the same speed, then you almost think that other train is like at rest, maybe even, right? But if you replace one of these trains with light, then you would still experience the speed of light as the speed of light. You would not experience speed of light as being less, okay? Just because you have a speed. So this this thing, the train stuff that I said, we understand that from Newtonian mechanics. The light stuff I said, we actually get that from electromagnetism, but we just hadn't digested that that is really the case. The speed of light being a constant of nature actually falls out of electromagnetic equations, okay? Maxwell's equations, etc. So late 1800s, we kind of had equations for electric and magnetic fields from which we can derive that the speed of light in vacuum is a constant. But the fact that the speed of light in vacuum is a constant really, really shapes physics in a way that now we get relativity out of it, where now we get relative nature of space and time, and mass energy equivalence is the work of Einstein in 1905, okay? The insights he drew from by being an extremely good student of electromagnetism and just in general being an advanced researcher, the insights he drew from what he knew then, and not getting sort of distracted by all the ether stuff that they thought at that time, and instead developing special theory of relativity. That is where his genius really was, in 1905. Okay, so he had to go against the grain in order to do that, because he had studied Newtonian mechanics, like all good students, and he had studied electromagnetism, and he realized, oh, there is a discrepancy between these two things. And realizing those things, that's tough, because people take a lot of things for granted. Realizing it and then doing something about it and making your own whole, theory about it, that's another whole level. So anyway, that's what he did. And so really good job. From this, he was able to extract a principle, the constancy of the speed of light. Last, he was able to formulate the symmetry that unified space and time, the Lorentz transformation. So he was able to also find some symmetry between space and time, of course, which is part of the special theory of relativity, and goes towards general relativity as well. So see, he is used to finding symmetries. He has found success with symmetries, successfully finding symmetries, and also finding success in symmetries. Symmetries helping him out, symmetries of nature helping him out. So he relies on a nature which has these beautiful symmetries. So he was kind of looking for that in terms of this topic as well. And this is where it was a little, he was ahead of his time. First of all, some of the things were just not known. Some of the things are still not known, that he would have needed to really unify those things. And second of all, sometimes maybe nature is a little ugly, according to Einstein, and maybe you cannot quite have everything as beautiful, or maybe you need to walk the ugly path first and take 100 years to develop quantum mechanics, and see where that goes before you can kind of revisit beautiful ways of unifying the two. Okay, so I don't know, right? The unification we speak of here is still not done. So what he was trying over 100 years ago is still pending. Okay. Similarly, with general relativity, he had a picture that gravity was caused by the warping of space and time. This picture exposed the fundamental contradiction between Newton's gravity, where gravity traveled instantaneously, and relativity, where nothing can go faster than light. So now he also went against the grain and basically went against Newtonian gravitation. Now remember Newtonian gravitation. Newton is the apple falling from the tree guy. He is the father of gravitation. So to go again, Einstein is doing something ridiculously difficult and rebellious, but also just magnificent, which is he is challenging Newtonian gravitation, which had stood for years and years, I think a couple of centuries, if I'm not mistaken. So that too is a huge deal. So when he came up with general relativity, which is the upgraded, updated, corrected gravitation theory, that too is really big deal. Okay. So anyway, from the picture, he extracted a principle, the equivalence principle, that accelerating and gravitating frames obeyed the same laws of physics. Last, he was able to formulate the generalized symmetry that described accelerations and gravity, which was general covariance. That described accelerations and gravity, which was general covariance. So more math, more symmetries, more beauty, and a complete makeover for gravitation is what he did with general theory of relativity. And he extended relativity to be more general now, including accelerating reference frames and gravitation, not just inertial frames. Okay. Hi, Alice. You're here. Newton and Einstein were beyond most people. Both were amazing, right? But I wanted to make the point that um, you cannot, like, these things were not easy. Like, can you imagine going against Newton? Like, can you imagine going against something that had stood for a few centuries? That's what she did, or that's what he did, Einstein, right? Did I call him a she at one point? Whatever. Sh- sure, he wouldn't mind. But um, he really went against Newton, the apple falling from the tree guy, and redid gravitation. But of course, Newtonian gravitation stands as an approximation. It's just that the more accurate theory is general relativity. So, but that's really cool. The problem facing Einstein now, so now that the relativities are done, and he's looking for unification between relativity and quantum mechanics. Now he's facing a different challenge, and you have to understand his approach. This is why I've been kind of highlighting that. The thing that he has relied on is being able to imagine these things, being able to do thought experiments, finding symmetries of nature, doing beautiful, elegant math, where nature is beautiful. Nothing is ugly. There's no jungle of particles, which is what quantum mechanics ends up being. So this is where it was not only that some of the information was missing to him, but also it was really hard, I think, to sort of resolve things with a world that was not so pretty. Okay. The problem facing Einstein now was truly daunting because he was working at least 50 years ahead of his time, if not more. In the 1920s, when he began work on the unified field theory, the only established forces were the gravitational and electromagnetic forces. The nucleus of the atom had only been discovered in 1911 by Rutherford, and the force that held it together was still shrouded in mystery. So, as I was telling you, along with general relativity and whatnot, people, the fathers of quantum mechanics, were hard at work with developing quantum mechanics and making many discoveries in quantum mechanics, which led to so many new particles, etc. But a lot of things were not known before. Like, we didn't even, like I was saying, like, we didn't even know about the nucleus. We didn't even know about the neutron till what, like 1932? That guy James Chadwick, right? Somebody confirmed that. So, like, I mean, it's basically like so much information was missing to him, the person who was trying to unify everything. Well, to unify everything, you should probably know about everything, and knowing about everything was also hard. It's not fair to say, oh, you should know about everything, right? It's difficult. And yeah, he was looking for symmetry, and he was looking to unify the fundamental forces, but two of the four fundamental forces were kind of missing to him at that time. Okay. Thank you, Alice. I saw your message. Good luck with your research, by the way, in Italy. Really excited for you, and you should join the live whenever you can. No pressure, always lovely to have you. Alice here is doing research on dark matter. Oh, thank you. Thank you guys for all your support. Really appreciate it. Stephen Hawking? Stephen Hawking was the freak? I don't think so. I think he was pretty normal compared to Einstein. Mm, lol. You guys are funny. I should mix it up, maybe. Thank you for subscribing. Oh my gosh. Thank you, Alice. Thank you, Gordo. Hi, Space Time. Hi, Scott. Science teacher. Aw. Thank you to all the supportive comments. Thank you, thank you. A lot of them are saying I'm pretty. Somebody said to me earlier today that you're pretty enough to be famous, but I'd like to think that I'm a bit more than that. Also, can we get 80 likes? Ah. Welcome to Philippines. How are you, my lovelies? Pretty enough to be famous? Alice, you do help me so much. Einstein came after Galileo. So the thing is, I read something about Galileo and Einstein. Galileo is, the father of astronomy. I do believe we call him sort of the father of modern astronomy, of course. I mean, he started to really give us the idea of like modern observational astronomy with having a telescope and everything. But we all rely on the people that came before us. If Newton didn't work on everything he worked on, then there wouldn't be something to upgrade and update and correct later on, right? So, what I mean is that it's difficult going against the grain. It is difficult to have those original thoughts that then might end up correcting a long-standing theory. But at the same time, that is kind of what science is. All the new scientists are standing on the shoulders of giants, learning and understanding what's been done already, and doing their own journey of research and figuring out, oh, well, this doesn't make sense, or they come up against a question that they have to answer, and in doing so, they might have to overturn something that was well established. But at the same time, that's why we all always have to have a sort of a student mentality. We have to be really good students first, okay? Like if Einstein wasn't a very, very good student of electromagnetism, then he wouldn't have caught the thing about the speed of light being a constant. If he wasn't a very, very good student of Newtonian mechanics, then he wouldn't have caught certain discrepancies, which ended up telling him about also the speed of light being a constant and how that gives us relative space time, blah blah. So he was a great I'm not sure exactly how he did in school. I think he was like pretty good. I know he had some difficulties getting like a permanent job after grad school, but I know some of his schooling was like in Switzerland where it was better. I think he didn't like school in Germany. It's all in this book, by the way. I'm just kind of quickly remembering some things, which are hopefully I'm saying it right. But basically, I'm not sure exactly how he did it in formal school, but the thing is, in his own way, as a researcher, there is a classroom student and then there is a researcher. But as a researcher, he was a very, very, very good student of everything that was done before him. And that's basically what you have to do. See, there is a whole portion of science called literature review. Sometimes when people say nowadays, research it on Google, they actually mean about this portion of research. This is called literature review, where you basically have to learn, study, and review all of the literature or all of the things that has been done before. And you actually, cite those literature in your work, and you can agree with it, disagree with it, do something new, show something new, prove it out, blah blah blah, right? So really, when we are looking up things on Google, it is actually a lit review. It is not really research, because research is more than that. Lit review is the first step of research, and then you actually do more things to then progress your field. And once you've progressed your field and you have written a paper on it, which is peer reviewed, and you've fought with the reviewers and cried tears of blood from both eyes and thrown up on the paper, then you've done research. So hopefully that's very encouraging news to all the up and coming scientists. And so looking things up on Google is not research, it's lit review. And I just explained to you what research is, okay? So this crying the bloody tears, this is what Einstein did, okay? This is what he did with studying everything before him. So don't say that he didn't give credit to Galileo. That would be very weird if he didn't. You know what I mean? He is a peer-reviewed author, after all. I think you can look up his papers in the physical review letters or whatever other journals he might have written in. Poor guy, don't say anything about my Einstein. And peer review, obviously a big part of it is citing and giving credit. Now, I'm not saying that giving credit is completely perfect either. I know a lot of women were not given credit, for example. There's a lot of that as well in the history of science. So, but hopefully that makes sense with what the scientific process ideally is. But yeah, I wouldn't call using what Galileo did to be really stealing from Galileo, because Galileo came before, so it's fine. You can also use what Galileo did and discover something. You can how about so here's something you could, in fact, I mean it seriously, something that you could contribute to that Galileo started, and please do credit Galileo when you write this paper, is Galileo discovered the moons of Jupiter, right? Am I tripping, or is that correct? Galileo did discover the first the Galilean moons of Jupiter, right? Am I crazy right now, Alice? Correct, the Galilean moons. Thank God. I had to my brain was in a different dimension, so I was like, wait a minute, which planet was it? Jupiter, right? So Galileo just discovered the Galilean moons of Jupiter, some of these moons of Jupiter. So now, some of those moons, like Europa, is a great topic of research at this time. Europa has maybe potentially these subsurface oceans and whatnot, and they're doing all kinds of things to figure out more information about Europa. So when you could go and work on one of the moons of Jupiter, and please do credit Galileo for seeing them for the first time, So that's what I mean. You know what I mean? Once you're in Einstein's shoes, you can critique him. Once you're in his shoes and you're doing research and you're advancing science and you're advancing the field, don't forget to credit Galileo. Okay? Hope that helps. All right, we'll keep going. So the problem facing Einstein was now truly daunting because he didn't even know all of the things, for example, all of the fundamental forces and whatnot, because he's ahead of his time. One thing we realize, of course, the strong nuclear force, weak nuclear force were not discovered at that time. So he was lacking some parts of the puzzle that he's trying to solve here, okay? Furthermore, no experiment or observation exposed a contradiction between gravity and electromagnetism that would be the hook Einstein could grab onto. All right, so oh, thank you. Ganymede. It's Ganymede, right? Ganymede, Callisto, Europa, and Io. Yes. Hi, Kevin. Tesla's really cool. The guy, Nikola Tesla. Thank you for the likes. Can we get 80 likes? Ganymede, Callisto. No, you're fine. Europa and Io are the 4 moons of Jupiter that Galileo found way back in the day. And of course, now we have found many more. But back in the day, it was really important because he basically showed there was another whole world, not the Earth, that also had its own moons. Because Galileo was up against some very different and difficult times, right? He was doing science at a time where you were really persecuted for it and whatnot. So one of the big things that he contributed was he did some other things too. Like he found, our moon had imperfections. He found the phases of Venus. He found where Venus is a heavenly body, which is changing. So, that was important. And then with the moons of Jupiter, he showed that another whole planet or another whole world had its own moons. So we weren't so special with us having a moon. So now one of those moons, Europa, is a current hot topic of research, as I understand. For a number of years now, they've been trying to find out more information about Europa. Of course, these things are quite far. The Jupiter system is at 5.2 astronomical units away from the sun, which is about 5 times more distance than us from the sun. And so it's not easy to just like go and take a peek at Europa and things like that. But because of all the interest with, maybe subsurface oceans and whatnot, it tends to be a very important topic. So that's why I was mentioning, like, you could literally go work on Europa, and then when you do, please do credit Galileo, because he's the guy who first set eyes on Europa. Clipper mission. Oh, very nice. Milkshake Galaxy? Do you mean our own galaxy, the Milky Way galaxy? Thank you, Kevin. Somebody just requested that I talk about the milkshake galaxy. Do you mean our very own Milky Way? Europa and Europe sound quite similar. Yes. So I do like Europe and I do like Europa. Um, we did go to the moon. I must insist. Um, so so yeah. Anyways, you know, science is not done. Even you, us, all of us can still contribute to many things that are unknown in science. We're far from being done, and so keep on going. Okay, everybody. I hope that this is all very encouraging. And you really, if you get down to it, you know, you really can make a big difference. And whatever you do choose to work on, honestly, there could be no one else working on that. So such are the problems that exist. Okay, so let's see. Hermann Weyl, a mathematician who was inspired by Einstein's search for a unified field theory, made the first serious attempt in 1918. So now we'll come across a few sort of what do you call it? A few different attempts, okay, for unification that Michio Kaku is kind of mentioning here. Can we get 90 likes? So at first, Einstein was very impressed. So, you know, all these people that might have taken general relativity and sort of done something with it, probably wrote to Einstein and was like, "Hey, this is what I thought. This is what I think." Right. The nice thing about publication and letting the world know about what you did is that now it's no longer you that's thinking about it. Other people can take it and run with it. Other people can work on it too. And honestly, that is probably a good idea because at some point you want that to happen. You don't want to be sort of a monopoly on the topic because you want that diversity of ideas coming in and people kind of multiplying the effort versus just you doing everything, because you could also be wrong, you could make a human error, a mistake, and you know, and this is also why, like, people, you know, teach. They have students working on things, they have other completely other people working on things. At this point, we definitely realize, like, we need independent teams working on something really important in order for us to claim something. Okay, so anyway, Weil expanded Einstein's old theory of gravity by adding the Maxwell field directly into the equations. Then he demanded that the equations be covariant under even more symmetries than Einstein's original theory, including scale transformations, that is, transformations that expand or contract all distances. However, Einstein soon found some strange anomalies in the theory. For example, if you traveled in a circle and came back to your original point, you would find that you were shorter but had the same shape. In other words, lengths were not preserved. In Einstein's theory, lengths could also change, but they remained the same if you came back to where you started. Time would also be shifted in a closed path, but this would violate our understanding of the physical world. So, for example, it meant that if vibrating atoms were moved around a complete circle, they would be vibrating at a different frequency when they came back. Although Weyl's theory seemed ingenious, it had to be abandoned because it did not fit the data. In hindsight, we can see that the Weyl theory had too much symmetry. So Weyl went a little wild with his symmetries, which is fine. You know, it's okay for somebody to propose certain mathematics and then, you know, it can get shot down gently. I mean, not even gently. Maybe it can be shot down pretty rudely or pretty crudely, but respectfully, right? Scale invariance is apparently a symmetry that nature does not use to describe our visible universe. Then in 1923, another story. Now it's Eddington. Now, Eddington we have mentioned before. I don't like him for a number of reasons, but we'll see what he had to do. Eddington also caught the bug in 1923. Inspired by Weyl's work, Eddington, and many others after him tried his hand at a unified field theory. See, this is what I'm mentioning about when someone does something, even if it's wrong, it still provides some value in other ways. See, Weil spent a lot of time. Weil spent a while on developing the mathematics, having those symmetries, and then he came up with something which was a kind of wrong. But all of that work he did was now motivating others to pick it up and play with other types of symmetries to see if they can contribute, right? So when somebody does work and publishes, they are actually opening it up for others to contribute. So you shouldn't expect everything to be done by you. You have to let others contribute as well. And that is part of the science as well, you know. So that's nice that Weil did that. Like Einstein, he created a theory based on the Ricci curvature. So this Ricci thing we discussed earlier when we were setting up some math for general relativity. But anyway, so he also utilized that Ricci curvature, but the concept of distance did not appear in the equations. In other words, it was impossible to define meters or seconds in his theory. The theory was pre-geometrical. Only in the last step would distance finally appear as a consequence of his equations. Electromagnetism was supposed to emerge as a piece of the Ricci curvature. The physicist Wolfgang Pauli did not like this theory at all, stating that it had no significance for physics. Einstein also panned it, thinking it had no physical content. But what really rocked Einstein to the core was a paper he saw in 1921. Now, this is the one that I have been mentioning, which is sort of the precursor to the string theory, okay? Hello, ¿cómo estás? The ring is actually a brand deal. But the live is about physics anyways, so we don't have to focus on the ring. Unless they pay me more to show it. I just wear it now because I like it. Clears throat. Spin up, spin down. Hey Joe, hello. Somebody's talking about Mars. That's good. Thank you guys so much. Let me actually take a small break to see the time. And I might have to finish tomorrow, wrap this up really soon here, because I'm looking at the time and it's a little late and I do have to wake up relatively early tomorrow because I have an appointment. Whoops, let me put the password in again. Oh God, my fingers are so cold I can't even type the password. It's fine. Let me finish up the current section and then we will wrap it up and keep going tomorrow. Thank you everybody, by the way. Um. Oh, thank you, space-time entanglement. And thank you, space-time entanglement. I'm reading one word ahead of what I'm trying to read. Pluto is still a planet. No, planet. Dwarf planet. Pluto is a dwarf planet. Okay, let me read off the top fans. Okay, number 1 is J. Manuel. Thank you, J. Manuel. You're still number 1. Thank you so much. Number 2 is Steven Sky. Number 3 is My Music Gen X. Number 4 is IMMC Guy. Number 5 is Big Daddy Rod. Number 6 is Alice. Thank you, Alice. I got your message the other day. I think I already mentioned it, but good luck in Italy, and maybe I should come visit you because you'll be so busy. So I don't mind learning more about your work. Number 7 is Sam. Number 8 is Data Classed. Number 9 is Jay Franks. Hello, Jay. Jay Franks is in Italy. There you go. Number 10 is Derby Byron. Number 11 is John T. Number 12 is Space Time Entanglement. Number 13 is Mr. G. Number 14 is Mr. Drew. Number 15 is DFGCD. Okay. Thank you all so much. Oh my gosh. Scott. Thank you, Scott, for the super chat. Scott Romer has done a scooper chat. Scott Romer has done a scooper chat. Thank you so much. Indeed. Thank you for the super chats and the gifts. Let me finish up and then say goodnight to everybody, okay? All right. Let me read this part about the Kaluza-Klein stuff, and then we will continue tomorrow. This part is very important, especially when you understand and link it with superstring theory. Okay, so what we're seeing here is that after the birth of general theory of relativity, a number of people realized what Einstein was trying to do next with unification, and also tried to contribute. They were playing with maybe adding in more symmetries, doing the math differently, expanding on what was done already with general theory of relativity, and they were trying to contribute. So we saw the Weil contribution, we saw the Eddington contribution, and then there's also Kaluza and Klein. Now, these two people are going to prove very important, actually, in sort of establishing a foundation for superstring theory, which comes later. Okay, so let's see what they did in short. Okay. By the way, guys, can someone help me with my super chat goal? I did make one, right? Happy dancing for you is the when I meet my goal. Thank you so much. There's no pressure. If you're a student, don't worry about it. But if you're able to support the channel, then I do appreciate your help very, very much. Thank you so much. Okay. So what really rocked Einstein to the core was a paper that he saw in 1921, written by an obscure mathematician, Theodor Kaluza. So this guy Kaluza wasn't very well known at that time. From the University of Königsberg, Kaluza suggested that Einstein, who had pioneered the concept of the fourth dimension, add yet another dimension to his equations. So basically, this guy is taking the mathematics of general theory of relativity, which is already in a different geometry already, because it has one extra dimension. It includes space-time, so the 3 space dimensions and the time dimension, and it is done in that 4-dimensional kind of way. So he's taking that and wanting to extend it a little bit and add one more dimension, which is not too terrible, right? So, but it is extending what Einstein had done, and so it is new. Kaluza suggested that Einstein, who had pioneered the concept of the fourth dimension, add yet another dimension to his equations. Kaluza began by reformulating Einstein's own general relativity in 5 dimensions, 4 dimensions of space and 1 dimension of time. This takes no work at all, since Einstein's equations could easily be formulated in any dimension. Then, in a few lines, Kaluza showed that if the fifth dimension is separated from the other four, Einstein's equations emerged along with Maxwell's equations. In other words, Maxwell's equations, the horrible set of 8 partial differential equations memorized by every engineer and physicist, can be reduced to waves traveling on the fifth dimension. So it must have been quite a moment for Kaluza when he discovered that, right? Imagine trying to unify two things and then you just do one thing to extend the mathematics, but of course it takes work, and you get the unification, you get the result that you were kind of looking for. So in other words, Maxwell's equations, the horrible set of blah, 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 can be reduced to waves traveling on the fifth dimension. To put it another way, Maxwell's theory was already hidden inside Einstein's theory of relativity if relativity were extended to 5 dimensions. Now, Einstein did not suggest relativity to be 5 dimensions because he wanted it to be rooted in the physical world. The physical world is 4 space-time, the 3 space and 1 time dimension. And being somebody who was very intuitive, wanted to explain nature and the physical world with, the simplest way possible, he did it with the 4 space-time. But then mathematicians, they're fine with basically extended the math of something without maybe always having a physical motivation. And so someone like Kaluza, therefore made some progress by just playing with the mathematics and extending it to one more dimension, which was really interesting. So Einstein was surprised by the sheer audacity and beauty of Kaluza's work. He wrote Kaluza, "The idea of achieving unification by means of a 5-dimensional cylinder world never dawned on me. At first glance, I liked your idea enormously." A few weeks later, after studying the theory, he wrote, the formal unity of your theory is startling." In 1926, the mathematician Oscar Klein, so this is the other guy, Klein, generalized Kaluza's work and speculated that the fifth dimension was unobservable because it was small and possibly linked to the quantum theory. This is where we're getting real and we're seeing something new emerging. Okay, this is where the hope core is happening with extending GR. Okay, so they took GR, they took the geometry of GR, they took the mathematics of GR, which was already different than our usual mathematics and our usual way we do geometry, Euclidean geometry, usual math, Newtonian mechanics, etc. We already have done it differently in general theory of relativity, treating time as one of the dimensions, space-time, right? Having those 4 space-time kind of geometry already is making us sort of develop a whole new geometry. And now we have introduced a 5th dimension and we got the formal mathematical unification of gravity and electromagnetism. But then someone comes in and says that actually that 5th dimension doesn't have to be a big one. It can be a tiny one, an unobservable one. Maybe there are dimensions that we don't experience because it's teeny tiny. So now this teeny tiny-ness of that extra dimension also kind of makes you feel like it's not so crazy that it could be a thing. Can we get 90 likes? So, Klein generalized Kaluza's work and speculated that the 5th dimension was unobservable because it was small and possibly linked to the quantum theory. So this is also, by the way, a bit of that bringing in the quantum side of things, bringing in the small side of things, which relativity had discrepancies with. It's almost like this is the whole point. We were trying to unify the big and the small, and this is kind of doing that. This is that flavor of that. So Kaluza and Klein were thus proposing an entirely different approach to unification. To them, electromagnetism was nothing but vibrations rippling along the surface of a small, fifth dimension. And what is to say? Maybe human beings just don't experience all the dimensions, right? So this is where string theorists are basically unashamed to kind of need and require and demand more dimensions, because what is to say that there could be dimensions that we just don't experience, but they could be there, and they could be so tiny and curled up that we don't experience them, but they could very well be there. Now it doesn't help to that it doesn't, it doesn't help them that it cannot be proved because of the very tiny ness of these dimensions. We will find later on, right? Because this is still 1920s. String theory hasn't bloomed yet, but I'm just letting you know that this type of extra dimension mathematics is sort of a nice little birthplace for superstring theory later on, because it's taking general relativity and extending it and adding these extra dimensions. And the thought is that the extra dimensions could be there, maybe we just don't experience it, right? Now it makes it hard to test, but people can make compelling cases of that, right? And because the math works out so nicely and beautifully and whatnot. Now we will learn later on actually that properly doing the full string theory requires certain symmetries as well. And those symmetries also would have to be real and proved, etc. But on the face of it, it doesn't sound so bad, right? Like maybe there are some extra dimensions, maybe we don't experience them, and maybe this math is fine to do, and maybe we have our unification, which is what they were dealing with, just the two things, gravitation and electromagnetism. So that's really, really cool that by 1926 they had unified gravitation and electromagnetism by just adding one extra dimension to the already four space-time directions of GR. So also note, this is what I mean by the fact that the string theorists have to be pretty darn good at GR, because you're taking general relativity and extending it to include more dimensions. So you have to first be a really good student of general relativity. So these people, Kaluza, Klein, etc., they had to be really, really good students of the math of GR. Because if they were not, then they couldn't take it and extend it to the more dimensions, okay? So always go to a string theorist if you're looking to understand general relativity math. It should be like bread and butter to them. Okay. Do I have a mod in here? I see some of the messages going away. I didn't realize someone was here. Thank you for modding. Thank you for the gift. Thank you, son of Sammy Davis. Hello, Ben Abraham. Thank you for that comment. Love it. You make my tummy feel funny? Riding coattails of a genius. Exactly. Who counts down? Oh, I forgot. Fake. Edward Whitten. We talked about some of his work as well. When we had, I forget we have talked about superstring theory quite a bit. There were a few books that we covered superstring theory from, And we had a nice little paragraph from, at least a chunk from Edward Witten in there, okay? Thank you, J-Dub, for the flower. Okay, I'm going to look at the chat really soon. Let me finish up this little section. So, this is a really cool analogy. Listen to this, and then we will finish up and look at the chat full time before going to bed, okay? So about this small fifth dimension, okay? A little explanation of that small fifth dimension. As much as I don't like that string theory or this theory is not testable, as an experimental scientist, I really don't like that part. But at the same time, I have to say that the extra dimensions that are curled up and small are kind of cute. Listen to this. If we think of a fish living in a shallow pond, swimming just below the lily pads, the fish might conclude that their universe was two-dimensional. Aw, poor fish. They can move forward and backward, left and right, but the concept of up into the third dimension would be alien to them. If their universe was two-dimensional, then how might they become aware of a mysterious third dimension? Imagine that it rains one day. Tiny ripples in the third dimension move along the surface of the pond, and they are clearly visible to the fish. As these ripples move along the surface, the fish might conclude that there was a mysterious force that could illuminate their universe. Similarly, in this picture, we are the fish. We conduct our affairs in three spatial dimensions, unaware that there could be higher dimensions existing just beyond our senses. The only direct contact that we might have with the unseen fifth dimension is light, now viewed as ripples traveling along the fifth dimension. Now, of course, there are other ways of describing light. The formalism for light, you can rely on electromagnetic wave theory. You can do some particle physics of light with the photons and whatnot. So I also wanted to mention that if you don't like string theory and these extra dimensions, just know that there is a whole world of quantum mechanics and particle physics that was developed without really doing string theory or a classical theory to explain any of it. If you're more of an experimental person who likes to measure and discover more particles and new things, there is a reason why quantum mechanics and particle physics have been so successful in all of that, right? And there's a reason why the physics of the small, quantum mechanics, does a great job at that scale. But some of this unification stuff, where this sort of more classical and more elegant symmetry-y way of understanding things can also be fun sometimes to think about, just to imagine that maybe there are dimensions beyond what we can sense, beyond what we can experience, just like the fish in that pond under the lily pads and their two-dimensional life. Maybe we're like fish, and maybe there are extra dimensions that are like ripples in our reality, which we don't fully sense, but we see something. So, this type of thing can be also valuable to understand and have an open mind towards, especially as we tackle new topics and do new research going forward. Who knows, you might have to require some extra dimensions in your own research if you are trying to explain something new, okay? So keep that in mind, that there is always that. Without discovering these extra dimensions, superstring theory has been requiring them for quite some time now. So if you need to, go for it. You have my blessing at least. But I do like quantum mechanics and particle physics as far as what I would probably pursue myself. But at the same time, I like to learn about other things too. Okay, so that was the topic for tonight, and with that we are kind of done with the reading and the explaining, but I will look at the comments and can we get 100 likes? And thank you so much for all the hearts, emojis, and such. I will look at some of your messages and comments and appreciate everybody that joined. Thank you. Hello, the boy Kaj Zon. Soul Snatcher. Okay, I hate people who love to hear themselves talk. Hello, Josh. You're very pretty. Hello, Felix. Hello, Ishan. Hello, son of Sammy. I know the math, says Ferguri. Thank you, Joe. Bartozzi says, I like the reading. There's only up. Love your earrings. Thank you, son of Sammy. Just as a guitar string produces different. I love that. Thank you, Ben Abraham. I have not seen the movie Thunderbolts. Hello, iCycle. Hello, 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 everybody. Hi, Gary. Hi, Rap. Hi, Michael. Hello, Michael, again. In other words, with our five senses can see more dimension. Is anything really above us? There's space. So the fish thing was an analogy. It doesn't have to be like necessarily above us, just a dimension that we don't experience. Could be the extra dimensions that they're in this case, Kaluza and Klein proposed just one extra dimension. When we move on to superstring theory, they propose 6 or more extra dimensions, 6 or 7 extra dimensions. And so you can see how actually Kaluza and Klein were being pretty conservative. They were not being that crazy with just the one extra dimension. When you start to demand 6 or 7 extra dimensions, then it sounds much more complicated. But that's what superstring theory does. And so, you know, but the point is for these people, the people who are kind of proposing or requiring these extra dimensions, the point they're making is that there could be extra dimensions that are present that we don't experience, and they're kind of doing the math to describe it out. And finding certain nice discoveries or important symmetries. Hello, Timed Out. Hello, Nikki. Did you like it, Joe Bartozzi? I'm glad you're here. I'm glad for the people that are really enjoying this topic. I know how you feel. I feel the same way. And even after, you know, studying this for a long time, I still get very excited about this, all of this. So thank you for joining and sharing in my excitements. Space-time entanglement is saying it was wonderful, Wendy. Thank you. Thank you, guys. Please do like, share, subscribe, and keep coming back to these lives. We have many of these. And also, if you're new to the channel, then go and check out the other episodes under the live tab of the channel. There's many, many to look at and listen to in the background while you do other things, maybe. Somebody asked, do you think there are hybrid dimensions? Hybrid. I feel like that sounds kind of familiar, but what do you mean again? Hybrid? Like both big and small? Or, as far as I understand, in string theory, the extra dimensions are all curled up and small. I don't know about hybrid. Yeah. Yeah, somebody, Ben has pointed out, string theory remains controversial because it has not yet produced a testable experimental prediction that can be verified. I know the current technology really does not support that. Hello, Cosmil. The name of the book is Einstein's Cosmos by Michio Kaku. Hi, Ishan. Hi, Nick. Thank you. They were all intimidated by Witten. I mean, I could see that. But, I mean, physicists are intimidated by each other, I think. Are you on Facebook? Yes. All my other social media are linked on the description of this channel. But in general, my username is the same as the username here. OindryB is my username on YouTube. And that's my username on Instagram, on TikTok. And you'll probably find my Facebook too, if you use that. Thank you for finding me on other things too. Hello, Terrible Icon. Hi, Luna History. Thank you again to J-Dub. Thank you to Scott. Hi, Felix. Most of these comments are very supportive. Thank you. Hi, King. Hi, Nodelam. Space is not put there. That's called for. Oh, somebody here doesn't believe in the moon landing. Got it. I was wondering what the hate was all about. That's okay. That's okay. I get a few of you every time I go live. You know that, right? Thank you, Chance. Is it respectful to say you're a cutie? Thank you. Hello, DFGCD. Your username is kind of hard to say, but I try. Hi, Matt Clements. Oh God. People's comments about the fifth dimension are funny. Some of them I can't read out loud. You guys are naughty. Very naughty. The universe is connected. Okay. Alright, well, I went up as far as I could for the time being. I'm not a big fan of science fiction, actually. I like science more than science fiction. More of a sciencey girl than I'm a sci-fi girl. I mean, I like some science fiction. What a crowd. Well, as long as there's a crowd, I'm happy. Doesn't have to be totally supportive. But even negative comments are actually kind of supportive. Well, I was reading a comment about the cutie thing. But yeah, is it respectful to say I'm a cutie? Star Trek? I think I like Star Wars more. I loved Interstellar, and I think I like Star Wars more. I'm a Harry Potter girl. When it's fiction, then I want it like really fiction. I want it to be crazy. I want magic. So growing up, I read a bunch of like, you know, Enid Blyton, a children's author in England. So I read a lot of English authors, Enid Blyton, you know, Jane Austen, so like romance, murder mysteries, Agatha Christie, Sherlock Holmes. So, you know, the science brain part is not necessarily overlapping with all of my, you know, I mean, science is involved in those things too, but like, it's not that I only want to do physics and science and that's all I eat and breathe all day. I have other interests. So like, I like I always enjoyed these topics that, you know, I talked about with you today. It was a huge interest of mine, a passion, something I wanted to like learn more about and pursue and study and become, you know, something. But for fun, what I read more were probably like adventure stories as a kid, like Famous Five and, you know, the Five Find Outers, Enid Blyton, a lot of Agatha Christie. Like I literally read every Agatha Christie book in the library, and I think I've read all of her books at this point. As far as the murder stuff goes, so you know, murder mystery is a big fan. I'm a big fan of that. So I also like the corresponding movies. So I'd rather watch a murder mystery movie than a sci-fi movie, probably, or like a romance movie than a sci-fi movie. But Interstellar was really good, and I love the music of the movie. Yeah, I'm more of a, and then Harry Potter. So when Harry Potter, or I should say Potter, came along, I used to like wait for those books to come out and read them. And now I watch like all the plays, I saw all the movies. I'm more of that than I am a Star Trek. Definitely not a Star Trek. Like if someone makes me watch a Star Wars or a Star Trek, like if a friend wants to go, then I'll go with. But I probably won't initiate a Star Wars or a Star Trek. I'm a Potter girl, yeah. I'm not a fan of sci-fi and that much. Probably less of a fan than most people. I love Shakespeare. I grew up with Shakespeare as well. Enid. Hi, Risi. Enid Blyton. Sorry. Thank you, Risi. That's all you're good for tonight, apparently. Enid. A baby is smarter than an adult. Okay. Hello, Leroy. Hello, Jeffrey. Hello, Arwin. Enid. I'm so used to saying it wrong that it's hard for me to change the habit now because I've been reading her since forever ago. So, Reese, you might have to remind me again. Harry Potter. I have seen a Star Trek show. Got technical skills and super technical living in Mars. Thank you. Thank you everybody for all your likes, shares, subscribes, hearts, emojis, comments, chat messages, gifts, and super chats. Really appreciate you. If you want to do a super chat, last call. Really appreciate your support. Oh, Josh has done a deer. Oh my goodness. Josh Bills 6575 has done an oh dear. Oh dear. An oh dear. I love it. Thank you, Josh. Let me see. Josh Bills 6575. Oh dear. Oh dear. I like it. Oh dear again. Ah dear. Again. I will heart it. Thank you, Josh Bills, for an oh dear. Oh dear. Dear. Oh dear. Oh dear. I used to read Blyton when I was little too. Oh, Reese and I read the same author. He's British. I am not. Josh has done a, what is this? A laughing disco. Thank you, Josh Bills, for the laughing disco. That was really fun to watch. Can you do it again? That was really... I was trying to find the button to heart you. That was really fun. Thank you so much. Josh has done a laughing disco. Oh, thank you, Josh, so much for the laughing disco. Reese and I both read Enid Blyton, apparently. He just corrected me that it's not Enid Blyton, it's Enid. Enid Blyton. What's your favorite Enid Blyton, Reese? I read it because I grew up in India, and Reese read it because he conquered India. How dare you, Reese? You stay in your corner. Oh my gosh, thank you again for the laughing disco. I love it. I love it. Sci-fi is always number one. I know you guys love it. I made you yawn. Yeah, time for bed. Time for bed, maybe? Bed? Hi, beautiful. How are you doing? Hello, Pedro. Shalom to Ben. BB&J snacks. So tonight, I am all good on snacking actually because I ate a gigantic dinner at a Nepali restaurant. So tonight I went, like, first of all, I did the gym. I was working, I was at the gym. And then I took the bus. Like I did my gym routine a little bit different, like different timing. And I took this bus back. And then I took another bus to come home. But it dropped me off right next to my favorite restaurant because it's like the specific bus wasn't there and I took another one. And now I'm like next to this Nepali restaurant and I'm like, I have to eat here. And I was hungry. So I ate a huge meal. A huge meal. So I'm good on PB&J snacking. I'm probably good till like tomorrow. My stomach is very full and very happy. Yay. Thank you for the gifts, my darling friend Josh Bills. What is a groip? I don't know what that is. Do you believe in free will or think that the starting conditions? I believe in free will. What? I believe in free will. Been watching a thing about Einstein and Brown in motion earlier. See? What's your question about India? Are you married? No. I ate Nepali food, a mutton thali. I ate a mutton thali. It had veggie, dal, rice, papad, salad, and mutton, and cauliflower. Hi, Hypernova. Hi, Alpha. Where am I from or someone else? 3 boyfriends. Hello, Desiree. Desiree, you're being a little sketch right now. Are you in California? Okay, I actually never finished my drink. I'm going to warm it up again and sip it here with you guys and drink it before I log off, okay? Ooh, thank you, Theo. Theo Davis did a gift, thank you. Hi, Magma. Hello, C. Brian. My name is in my username, Ben. Hello, Auntie. Hi, Wild. How have you been? Oh, God. If you're joining, please do rewind to see the full lecture. Number 1 top fan right now is Josh. Thank you, Josh, for the gifts. Really appreciate you. Number 2 is Scott. Number 3 is Ben. Number 4 is for Gory. What do you mean? There's women in here? How do you know? Hi, Anshuman. Wild and fresh. I'm on a bit tired from food shopping earlier. I too find grocery shopping to be immensely tiring. Immensely. In fact, I hate grocery shopping. I try to get it delivered. Or not eat. I'm just kidding, I eat eggs and chickpeas. The chickpeas come in cans. It's just full of women in here. It's crazy. Never seen any men in this chat. What do you mean by that, Reese? What are you saying? Have you not had any sleep? Are you losing it? Hello, the boy. Lord Byron, have you been here this whole time? I never saw you before. Tell me why you bring up this ticket or topic. Which topic? Reese is saying there's never any women. I did check. And my YouTube is 80% men. I regret to inform you guys that, well, I don't know what I have done to deserve this. Let me check again right now, actually. Let me check right now. Let me check right now. Community? No, not community. Analytics. Audience. Age. Oh my god. Oh my god. Oh my god. Oh my god. Reese. Guess what my gender ratio is now? I mean, granted that some people give their phones and tablets to their kids, so like the age and whatnot, I don't always take it at face value. Like, say it's saying that people, so let me tell you the age ranges first. It's saying that I have some percentage of 13 to 17-year-olds. Pretty small percentage. Then 18 to 24, quite a bit. 25%, a lot. 35 to 44, a lot. 45 to 54, quite a bit. And 55 to 64 to 65 plus, those are all evenly spread. So some people just give their phones and tablets to their kids, and I feel like the kids are using their parents' accounts to come on my channel. So I don't pay attention to the age too much. But the gender... Reese, guess what the gender ratio is right now? Hi, Sean. Welcome to the channel, Anshuman. Can you subscribe? Oh, you were being sarcastic. That's right, you're British. I forgot. You can be funny. Reese, how's Charlie? Jeffrey is saying hello, 64 male. Hello, I see you. I see you. There is 10.6% of 55 to 64 on my channel. So you have lots of company. 10% are your age. Alice. I don't know many women interested in reading Michio. I read Michio Kaku when I was like 12. How come women don't read Michio Kaku? What do you even mean? What does that mean? You need to do more TikTok dance trends. I have a TikTok. I don't do dances there much. I do travel content there. I'll have to I'll check if my TikTok has women or not. What's kick? I don't know what kick is. What's the time? 3:13 in the morning. Thank you, Ben. Ben is saying we need channels like yours. Thank you. I really like what I'm doing. I hope that more and more people join. You need to do more TikTok dances. Oh yeah, I read that. Last time I checked, and the time before that I was a man. Hello, Blue Storm. Clearly you are. At one point, I actually used to have a lot of kids coming to my lives. Like over a year ago, I feel like a lot of the people were kids and they would be using their parents' accounts, and I would have a bunch of 35 to 44-year-olds in my analytics. But actually, these people, when they were talking, I was like, are you in 4th grade, honey? And they'd be like, yeah. They were all 10. Like, actually, they were all 10. Like, there was a time, I think there was a month. It might have been, no, it might have been the year before last year, summer. There was a time when every single day I would have a live with mostly kids who were 10. Literally all of them were 10. But they were joining from their parents' phones. So it made it look like they were 35 to 40, but they were 10. Are you guys 10? I don't think so. I think it's changed a lot since then, but so yeah, 64. I studied physics. Charlie's fine, thank you. He's a little cutie pudding. Oh, are you enjoying your little baby? I've read Alice in Wonderland. Hello, Anzonio. Hello, Smith. Kick is a streaming platform. Okay. Ooh, Kick. Okay. Hi, Lord Byron. Why do you want me to teach elementary school for a year? Maybe I will, but wouldn't I get sick a lot from the kids? Don't they have a lot of diseases? That's what I hear from my friends with kids. Just more chaotic. So this stream is about physics, and particularly we covered a lot of Einstein's work. If you want to rewind and see the whole thing, okay? Thank you so much. Whatever, well, I don't know if they give that information, but it's just the analytics telling me what accounts are there. The people who do give their age, this is that. Yes, people do tell YouTube their birthdays and stuff, I guess. I don't know all of y'all's like birthdays or anything personal like that, but I'm given some of the analytics to kind of tell me who my audience is. So the age one I really don't pay much attention to because, like I said, it could be a little bit skewed because people are using other people's TVs and phone tablets. Um, but the gender, okay, I'm gonna do a gender reveal. Thank you, RK. It used to be 80-20. It used to be 80% men and 20% women. Now it's 85.2% men and 14.7% women. It's even less. Hi, Priyanshi. Are you a woman? That's why I don't get super chats. Women give more super chats. You're a girl? Priyanshi, you're one of the few girls on my channel. Please like, share, and subscribe and keep coming back to all my lives. Thank you, honey. What do you think I can do to get more women? You already subscribed. Thank you, honey. My Lamb Stone. I'm a woman with 97% male subs. Oh, wow. So I have it better than you in that sense. Shoot. What is that like? Thank you, TD Malo. I'm on the toilet right now. Thank you for letting us know. They don't... What? They like relationship type stuff and bad-mouthing men? I don't think so. I don't think that's true. I do like murder mysteries. Steven! Steven! I have no women. Steven, can you get some women to join the channel? Please. Steven is one of my original men who joined. Steven, can you get your mom on here? Or your sister? Or Britney Spears? Or your other cousins who are female? Have you told your neighbors? Hi, Blue Storm. LawTube. So women want to know about the law? But I like physics. I don't think it's gonna be that I suddenly change my topic. I'm gonna do physics. Randy is saying I'm a woman. Oh, I do have some women. I do. Hi, Bill. Thank you, RK. Your topic is amazing. Thank you so much. Please do come back on my lives and watch all my videos. And please leave your comments on all of them too. RK. Hi, Matt D. It's mostly just men here who like beautiful faces and brains. Thank you, Matt D. Randy! You're not a woman? I knew it! I was like, that name? It must be that she's using her dad's phone. Are you your dad? I do science presentation, physics, and kitty cats. I'm texting back a client. I like a lot of different physics, theoretical and experimental. It doesn't make me sad, Bill. I'm drinking a warm malt. There's a lot of men like that, Reese, not just Indian. Priyanshi Singh, kaise ho aap? ठीक हूँ और आप? Okay. It's a classic malt. It's this thing, Horlicks, from India, from my Indian grocery store. You should use pretty visual aids like glitter and stuff. Glitter?